So what is, hybridization and why do we need hybridization? Um, if we were to look at carbon, all right, and the electron configuration for carbon, carbon is 1s2, 2s2, 2p2. And so if we were to look at, right, where those electrons are, right, and here's the energy, here's our 1s orbital, here's our 2s orbital, and here's 1, 2, 3, our 2p orbitals, and I've got 6 electrons. So 1, 2, 1, 2, and 1, and 2. So if we look at that, right, it doesn't really quite make sense on how we can explain how something like methane forms, right? Here's methane. Carbon forms 4 bonds. We know that because methane exists. And yet when we talked about how something forms a bond, we said, right, you basically need to have one orbital with an electron so they can share one more electron. So looking at this electron configuration of carbon, we would expect carbon to form 2 bonds. It could share an electron here, it could share an electron here. It couldn't share any electrons with the 2s orbital because that orbital is full. It couldn't share any electrons here with the p orbital because also, right, that orbital is empty. So we need to have at least one electron occupied in that orbital so that we can share one electron in another orbital. So looking at this, we're kind of having a problem in that carbon forms 4 bonds, and yet based on this, right, carbon should just form 2 bonds. So all that hybridization is just something that we came up with to explain how carbon can form 4 bonds. What orbitals is it using? Where are those electrons that it's using, that it's sharing? To explain how something like methane exists. And so all that hybridization is we're going to take and blend these orbitals together. So we're going to blend these orbitals together. Right, so we're going to mix together 1s orbital with 3 p orbitals. We mix these together. And now, right, if we look at this, if we look at the electron configuration of carbon, here's our 1s orbital. Now, I'm going to have 1, 2, 3, 4 orbitals. Here's my 2 electrons that were in the 1s orbital. Those are still there. But now, I have the same 4 electrons. I'm going to reassign those same 4 electrons. 1, 2, 3, and 4. They're not in an s orbital. They're not in a p orbital. They are in 4 identical sp3 orbitals. And we call them sp3 because that's basically saying, right, that it is 25% an s orbital and 75% a p orbital, right? And we got that from mixing 1, right? A quarter of these orbitals is an s orbital. 3/4 of these orbitals are p orbitals that we mix together. So that's all that hybridization is. It's something that we came up with to explain how can carbon form 4 bonds, right? Just because based on the electron assignment that it has, it shouldn't be able to form 4 bonds, and yet it does. So hybridization is how we explain where are these electrons? How can we form 4 bonds, 4 identical bonds, right? Because if we'll notice here, all 4 of these orbitals now, these hybrid orbitals, they are all the same. They're not an s orbital, they're not a p orbital, they are all sp3 hybrid orbitals. And it's not just for carbon, right? We do this for other elements as well in other molecules. Just to finish off carbon though, right? Another important thing, we know in this, right, when carbon has 4 bonds, right, it's tetrahedral. Well, now we have 4 identical electron domains. So now that we have 4 identical electron domains, right, the best arrangement in space, and I'm not going to be able to draw it that well, but the best arrangement in space for 4 electron domains is a tetrahedral geometry. So now we have 4 identical orbitals that can form 4 identical bonds with hydrogen. We know that's the case, right? All of these carbon-hydrogen bonds are the same length, they're the same energy, which means they need to be coming from the same type of orbital. So it's not an s orbital, it's not a p orbital. We blend these together. That's all that hybridization is. Literally just toss all 4 of these in a blender, mix them all together, and we're going to pour out 4 separate orbitals that are all identical now because we've mixed all 4 of these together to get 4 identical orbitals now that are sp3 hybridized. And it's not just for carbon, right? Other elements will hybridize. And so if we look at one more example, someone else want to answer that question? All right, we can look at water. We can look at oxygen. All right. So for oxygen, oxygen is 1s2, 2s2, 2p4. So here is my 1s orbital, my 2s orbital, and 1, 2, 3, 2p. Let's see. Got 1, 2, 1, 2, 1, 2, 3, and 4. So other elements hybridize as well, because if we looked at water, sure, we could explain the bonding of water by just looking at its electron configuration, because I could form a bond with hydrogen. Let me just change this color. I could form a bond with hydrogen. Well, it still doesn't show up that well. I could form a bond with hydrogen right here. I could share 1 electron right here, and I could share 1 electron right here. Okay, that explains the 2 bonds that oxygen could form. There's something wrong with that. There's 2 things wrong with that. Number 1, these p orbitals would be at 90 degrees from each other, and yet we know oxygen has a bond angle of like 104.5 degrees. The other thing about that is, yes, oxygen has 2 lone pairs of electrons, right? One there, one there. Looking at this electron configuration, these lone pair electrons would be in different orbitals. So they would be different. They would have different energy, right? They'd have a different, right? S orbitals are closer to the nucleus than p orbitals. We don't notice a difference between these lone pair electrons. So other atoms hybridize as well. So we can need a new color here, right? We're going to take these orbitals, we're going to hybridize, we're going to blend these orbitals together. So I'm going to take my s orbital, my 3p orbitals, we mix those together, we blend those together, and out of that, right, our new hybrid orbital, right, for every atomic orbital, and these are our atomic orbitals, for every atomic orbital we mix in, we're going to get out 1 hybrid orbital. So here's my s orbital. And now, because I mixed together 4 atomic orbitals, I'm going to get 4 hybrid orbitals out of that. They're not an s orbital anymore. They're not a p orbital anymore. They are sp3. And I can reassign the electrons, right? 1s, there's the 2 electrons there. And now I've got 6 electrons to assign. 1, 2, 3, 4, 5, and 6. So now that oxygen is hybridized, we've fixed both of our problems. Now, both of these lone pair electrons are in identical sp3 hybrid orbitals. So they would be equivalent, right? There wouldn't be a difference between those 2. And now that we're sp3 hybridized, right, we're back to that tetrahedral geometry, right? Because we've got 4 identical electron domains. So now that we're back to that tetrahedral geometry, right, we're back to something in the range of, 109.5 degree bond angles. Whereas if we were up here, our bond angles would be 90 degrees. We know they're not 90 degrees, right? They're a little bit less than 109.5 because of the lone pair electrons. But, right, we can do this with water. We can just say, okay, right, here's my oxygen. Here's my hydrogen, lone pair, right? And there we have water in the geometry that we know water exists, right? It doesn't have 90 degree bond angles. So we can explain, and we use this for more than just carbon, more than just oxygen, right? We use this for many atoms to explain the number of bonds that an atom forms. The geometry of that atom is through hybridization, blending orbitals together. Right, it's not too bad, right? It's just, linear should be easy because that's 180 degrees, right? Trigonal planar also should be pretty straightforward because that's 120 degrees, right? If you have a circle and you split that circle into 3 equal parts, right? 360 degrees divided by 3 is 120. Tetrahedral might be the only outlier, the only hard one at 109.5 degrees. Trigonal bipyramidal, right, is 120 around the equator, and then 90 degrees, right, axis to equator, and then octahedral should be pretty easy as well because an octahedral, right, we've got 1, 2, 3, right, we've got 6 electron domains and everything is 90 degrees. 90 degrees around the equator, 90 degrees from the axis to the equator for those bond angles.